Below in this lecture, I will answer two questions. In the first question, we find out the area of this green shape using two different methods. And in the second question, we find out the area of this circle that intersects with this right triangle ACP at those 2 points. So let's start with the first question. In the drawing, we have quarter circle AOB. We know that OB equals to 2 units in its length, AD equals to DO, and this is angle DCB, that is the right angle. Again, our task is to find out the area of this green shape. The green shape is actually the right triangle DCB. So we have to find out the area of this right green triangle DCB. So first of all, AOB is a quarter circle, and therefore this is angle AOB, that is the right angle. OB and OA, they are both the radii of the quarter circle, that equals to 2. So the radius OB equals to 2, and therefore the radius OA must be also equal to 2 units in its length. The radius AO, that equals to 2, has been bisected into 2 halves at point D. The first half AD is equal to the length of the radius over 2, that is to say it is 2 over 2, that is 1. And it is of course equal to the second half of the radius AO, that is DO, that equals to 1 unit in its length. In the next step, we implement the quadratic theorem on this right triangle DOB. Here by PT is the version of our quadratic theorem. According to the quadratic theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In this right triangle DOB, DB squared, that is the square of the hypotenuse, equals to DO square plus OB square. And again, in this right triangle DOB, according to the quadratic theorem, the following equation is true. DB squared, that is the square of the hypotenuse, equals to DO square plus OB square. DB is the missing side, so we have to set it, so it is DB square equals to DO square. DO is 1, therefore DO square is 1 squared, that is 1, plus OB square. OB is 2, therefore OB square is 2 squared, that is 4. So in total, if you found out that DB square equals to 1 plus 4, that is 5. So DB square equals to 5. Here we will take a root out of this equation and find again that the missing hypotenuse DB is equal to the square root of 5 units in its length. This is the hypotenuse DB, that is equal to the square root of 5 units in its length. In the next step, we will do a construction, that is to say, we will complete this quarter circle AOB to a circle. So completed this quarter circle to a circle, and in the next step we will extend the radius BO of this quarter circle by a straight line until it touches the circle. And when we find the touching point of the extended radius BO of this circle, this point is point P. BO is the radius of the quarter circle, so BO is a radius, it is absolutely a straight line. When you extend a straight line by straight line, the result BP is also a straight line. So BP is a straight line that touches the circle at those 2 points P and B, therefore BP is a chord. BP is a chord that passes from point O, that is the center of the circle. We know that any chord that passes through the center of the circle must be the diameter of the circle. And therefore, chord BP is the diameter of this circle. So, write it down. Chord PB is the diameter of the circle. The next step, we will extend, but before that, point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle, that is equals to 2. In the next step, we will extend the radius AO of this circle by a straight line until it touches the circle. And when we define the touching point of the external radius AO with this circle, this point is point Q. We extended the radius BO by straight line and we got the diameter BP. We extended the radius AO by straight line, we got chord AQ, that is, must be also the diameter of the circle. So I write it down, AQ is also the diameter of the circle for the same reason that PB is the diameter of the circle. So AQ is also the diameter of the circle. In the next step, we will extend side CD of this right time DCB by straight line until it touches the circle. And the question is where the extended side CD will touch the circle. We will assume that the extended side CD will touch the circle at this point, point N. So according to our assumption, we have here peripheral BCN This is equals to 90 degrees inside according to what is given in the question. Perifungal BCN subtend on this chord called Vn. And again, this is perifungal BCN. This is equals to 90 degrees inside according to what is given in the question. And perifungal BCN subtend on this chord called Vn. But chord Vn is definitely not the diameter of the circle. Why chord Vn is not the diameter of the circle? Because chord Vn doesn't pass for point O. This is the center of the circle. And any chord that doesn't pass for the center of the circle cannot be the diameter of the circle. So we have here contradiction to rule 5. Why? Because according to rule 5, any perifungal that equals to 90 degrees inside must subtend on the diameter of the circle. So this is perifungal BCN, that is equals to 90 degrees inside, and therefore perifungal BCN must subtend on the diameter of the circle. But perifungal BCN subtend on chord Vn, that is definitely not the diameter of the circle. So we have here contradiction to rule 5. Due to the contradiction to rule 5, we cancel the possibility that the extended side CD will touch the circle at point N. So the extended side CD cannot touch the circle at point N due to the contradiction to rule 5. In the next step, we will assume that the extended side CD will touch the circle at this point, point M. So according to our assumption, we have here perifungal BCM. That is equals to 90 degrees inside according to what is given as the question. And perifungal BCM subtend on this chord called BM. Chord BM is definitely not the diameter of the circle. Why? Because of the fact that chord BM doesn't pass through point O, that is the center of the circle, and therefore cannot be the diameter of the circle. So we have perifungal BCM that is equals to 90 degrees inside, and it still doesn't subtend on the diameter of the circle, and therefore it is a contradiction to rule 5. Due to the contradiction to rule 5, we conclude that the extended side CD will not touch the circle at point M. And therefore, we must conclude that the extended side CD will touch the circle at point P and not in any other point. Otherwise, we will have contradiction to rule 5. So the extended side CD touches the circle at point P. Now we don't have any contradiction to rule 5 because of the fact that this is perifungal BCP that is equals to 90 degrees inside, and indeed it's subtend on chord PB that is the diameter of the circle. Exactly according to rule 5. PB is the diameter of the circle according to what we already found out. PB is the diameter of the circle, so PB is the diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line PB at point O, Here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point O? We have this angle at the right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is the right angle plus this angle. So in total, the sum of those two angles must be equal to 180 degrees, and therefore this missing angle must be equal to 90 degrees in size. So angle AOP is the right angle. So in this right angle POD, according to the Pythagoras theorem, 2 square plus 1 square, that is in total 5 equals to PD square. That is the square of the hypotenuse. So PD square equals to 5. If we take out from the equation, we get that the hypotenuse PD equals to the square root of 5 units in its length. So in the next step, we will implement all 24 in our drawing. So I press quickly on all 24. All 24 is true in any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OB. Again, AO times OB equals to CO times OD. So in the drawing we have a circle. This is called AB that intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement 124 in our drawing. In our drawing, this is called AQ. Chord AQ is the longest chord in the circle because of the fact that it is the diameter. Chord AQ intersects with chord CP at point D. Why CP is a chord? Because of the fact that, first of all, CT is a straight line because it is one side of the granite line, the CP. When you extend the straight line by straight line, the result CP must be also a straight line. But CP is a straight line that touches the circle at those 2 points C and P, and therefore CP is a chord. So repeat again, according to all 24, chord AQ intersects with chord CP at point D. So all the requirements of all 24 are satisfied, and therefore can implement here all 24. All the requirements of all 24 are satisfied, and therefore can implement in our drawing all 24. So write it down. We shall find out that chord AQ intersects with chord CP at point D. Okay, again, we shall find out that chord AQ intersects with chord CP at point D. And therefore, according to rule 24, the following equation is true. AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. So, write it down. And again, according to rule 24, the following version is true. AD times DQ equals to CP equals to AD times DQ equals to CD times DP. AD is 1 times DQ. Point O is the center of the circle, point Q is the point of the circle itself, therefore Q is the radius of the circle, this equals to 2. So in total, DQ equals to 1 plus 2, that is 3. And it is equals to CD is the missing side, so leave it as it is, times DP is equal to 5. So in total, according to rule 24, we should found out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to the square root of 5 times CD. Here we divide this equation by square root of 5. We get that the missing side CD is equal to 3 over square root of 5 units in its length. This is the missing side CD. Is equals to 3 over square root of 5 units in its length. The next step, we will implement the Pythagoras theorem on this generator DCB. Here by PT is the ratio for Pythagoras theorem. In this generator and DCB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, is equal to DC squared plus CB squared. And again, according to the Pythagoras theorem, on this right hand triangle DCB, dB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. dB is equal to 5, and therefore dB squared is equal to 5 squared, that is 5. And it is equals to DC squared. DC is 3 over square root of 5, therefore DC squared is 3 over square root of 5 squared. That is actually 9/5. Plus CB squared. CB is the missing side, so it is this. So I should now know that 5 equals to 9/5 plus CB squared. Here we multiply 5 by 5 and then we divide it by 5 in order to come out of this number. 5 times 5 is 25 divided by 5. 25 over 5 is 5. So it changes nothing. So 25 over 5 equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation, and finally get that 25/5 minus 9/5 is 16/5 equals to CB squared. Here we take out all of this equation, and finally get that the missing side CB is equal to the square root of 16, that is 4, over square root of 5 units in its name. This is the missing side CB is equal to 4 over square root of 5 units in its name. Our task is to find out the area of this green shape. The green shape is actually the green right triangle DCB. Again, the area of the green shape is actually the area of the green right triangle DCB. And the area of this green right triangle DCB equals to the base DC times the height CB over 2. And again, the area of the green right triangle DCB equals to the base DC times the height CB over 2. DC is 3 over square root of 5 times CB is 4 over square root of 5 divided by 2. So total, the area of the green shape equals to the value of this expression. This expression equals to 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. Here 12 over 5 over 2. We will move 2 to the denominator of this expression, and get that this expression in total equals to 12 over 5 times 2. So this is 12 over 5 times 2, 5 times 2 is 10. So in total, the area of the green shape equals to 12 times. In terms of numbers, it is equals to 1.2 square units in its size. Then again, if you find out the area that you are looking for this question, the area of this green shape is equal to 1.2 square units in its size. So, we finish with the first method. In the next step, I present you how to find out the area of this green shape according to the second method. AOB is a quarter circle, and therefore this is the right angle, angle AOB is the right angle. OB and OA, the two are there of this quarter circle. Therefore each of them is equal to 2. The radius AO equals to 2 units in its length. The radius AO that is equals to 2 has been bisected at this point D. So each half of the radius AO must be equal to 2 over 2, that is 1. So the first half of the radius AO is AD, that is 1. And the second half of the second radius AO is DO, that is also 1. In the next step, we will complete this quarter circle to a semicircle. And we'll extend the radius BO by side line until it touches the semicircle. We define the touching point of the external radius BO with this semicircle. This point is point P. Point O is the center of the semicircle. Point P is the point of the semicircle itself. Therefore, OP is the radius of the semicircle. This is equals to 2. The radius BO, it is absolutely a straight line. BO is a straight line. When you extend that straight line by straight line, the result BP must be also a straight line. So BP is a straight line. BP is the straight line that touches the circle 2 points B and P. That touches the semicircle those 2 points B and P. And therefore BP is a chord. BP is a chord that passes from point O, that is the center of the semicircle, and we know that any chord that passes from the center of the semicircle or a circle must be the diameter of the circle. And therefore, PB is the diameter of this circle. PB is a diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point O? We have this angle, that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle PDO, this is the right triangle PDO. In the right triangle PDO, according to the Pythagoras theorem, 2 squared plus 1 square is 5, so 5 equals to PD square. We take a root out of the equation and we get that the hypotenuse PD equals to the square root of 5 units in itself. We already done it in the first method, but I could have done it anyway. The hypotenuse PD must be equal to the square root of 5 units in its length. In the next step, we define this angle DPO as alpha, and we focus on this right small triangle PDO. In the right small triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this value this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. that is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to alpha, and therefore angle alpha is also a common angle that belongs to both triangles. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that this is the small right triangle PDO, and it is similar to this big right triangle PCB according to angle similarity rule. So what the small right triangle PDO is similar to this big right triangle PCB. First of all, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself is a common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So we can find out that all the angles of this small right triangle PDO are corresponding equal to all the angles of this big right triangle PCB, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the right small triangle PDO is similar. This is the sign of similar to this right big triangle PCB. According to angle similarity rule. But again, we have to find out that the right small triangle PDO is similar to the big right triangle PCB according to angle similarity rule. And for the fact that the small right triangle PDO is similar to this big right triangle PCB, we will derive that the following relationship exists between their sides. We derive that side PD of this small right triangle PDO or side PB of this big right triangle PCB is equal to side DO of this small right triangle PDO over side CB of this big right triangle PCB, and it is also equal to side PO of this small right triangle PDO over side PC of this big right triangle PCB. So I write it down. PD over PB equals to DO over CB equals to PO over PC. Again, from the fact that the small right triangle PDO is similar to this big right triangle PCB, we derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle PDO over side PB of the big right triangle PCB is equal to side DO of the small right triangle PDO over side CB of the big right triangle PCB, and it is also equal to side PO of the small right triangle PDO over side PC of the big right triangle PCB. PD equals to the square root of 5 over PB. PB in total equals to 2 plus 2, that is 4. It is the diameter of the semicircle. So PB equals to 4. And it is equals to DO. DO equals to 1 over CB. CB is the missing side, so leave it as it is. And it is equals to PO. PO is 2 over PC. PC in total equals to the square root of 5 plus DC. But again, in total, if you found out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, therefore we will create equation 1 from those two sides that are equal to each other. According to equation 1, we will get that square root of 5 over 4 equals to 1 over CB. So write it down. According to equation 1, square root of 5 over 4 equals to 1 over CB. Again, according to equation 1, square root of 5 over 4 equals to 1 over CB. Here we will cross multiply this equation. Equation 1, and get that according to equation 1, 4 times 1 is 4 equals to the square root of 5 times CB. According to equation 1, if you found out that 4 equals to the square root of 5 times CB. Here we will divide this equation 1 by square root of 5. If I get that according to this equation 1, the missing side CB is equal to 4 over square root of 5 units in its length. This is the missing side CB is equal to 4 over square root of 5 units in its length. Those two sides of the equation are equal to each other, therefore we get the equation 2 from those two sides. According to equation 2, we get that square root of 5 over 4 equals to 2 over square root of 5 plus DC. According to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. So here we will first multiply this equation 2. So you get that according to equation 2, 4 times 2 is 8. So 8 equals to the square root of 5 times square root of 5 plus DC. So according to equation 2, if you found out that 8 equals to, look at the brackets of this expression, square root of 5 times square root of 5 is 5. And we have square root of 5 times DC is square root of 5 DC. So according to equation 2, we found out that 8 equals to 5 times 4 to 5 times DC. Here we subtract 5 from the equation and equation 2, and find that according to this equation and equation 2, 8 times 5 is 3, so 3 equals to the square root of 5 times DC. Here we divide this equation and equation 2 by square root of 5. If I get that according to this equation and equation 2, limits inside DC is equal to 3 or square root of 5 units in its length. So actually this is limits inside DC is equal to 3 over square root of 5 units in its length. Now it is very easy to find out the area of this green shape. That's the area that we are looking for in this question. The area of the green shape is actually the area of this green right triangle DCB. From the drawing it is very easy to see that the area of the green shape is the area of the right triangle DCB. And the area of this green right triangle DCB equals to the base DC times the height CB over 2. And again, the area of the green right triangle DCB is equal to the base DC times the height CB over 2. The base DC equals to 3 over square root of 5 units in its length times the height CB is equal to 4 over square root of 5 units in its length divided by 2. And again, we found out that the area of the green shape in total equals to the value of this expression. 3 times 4 is 12. Over square root of 5 times square root of 5 is 5 over 2. So the value of the area of the green shape equals to 12 over 5 over 2. Here we move to the denominator, this expression. We get that this expression in total equals to 12 over 5 times 2. So it is 12 over 5 times 2 is 10. And 12 tenths is 1.2 square units in size. And again, in both methods, we found out that the area that we are looking for in this question, the area of this green shape is equal to 1.2 square units in size. So we finish with the first question. The next step, I present to the second question and solve the second question of this lecture. Our task in this second question is to find out the area of this circle. So in the drawing we have a circle that intersects with this right triangle ACP at those 2 points. This is my side BC, This is equal to 1 unit in its length. This is 97 CP. This is equal to 4 units in its length. This is angle CB. This is a right angle. This is the common sub point P. Point P is the common sub point in relation to this circle. On this common sub point P, we have two tangents to this circle. Tangent PA and tangent PB. And according to all two, they are equal to each other. So I put quickly on all two. According to all two, the lengths of two tangents from common sub point to a circle are equal. In the drawing, we have a circle. This is the common sub point P. From this common sub point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule, two are equal to each other. They are equal to each other. So PA equals to PB. So we can implement rule 2 in our drawing. In our drawing, this is the common sub point P. For this common sub point P, we have two tangents to this circle, tangent PA and tangent PB. And according to all two, they are equal to each other. So if we follow the common sub point P, we have two tangents to this circle, tangent PA and tangent PB. And according to all two, they are equal to each other. This is to say PA equals to PB according to all two. But it is given as a question that the length of this tangent PB into that equals to 1 plus 4, that is 5. So can I say that the length of tangent PB equals to 5 units in its length? And from this equation, PA equals to PB equals to 5. We derive that tangent PA also equals to 5 units in its length. This is tangent PA that is equal to 5 units in its length. In the next step, we will implement the Pythagoras theorem on this right triangle ACP. Here by PT is a function for Pythagoras theorem. In this triangle ACP, according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. And again, in this triangle ABC, according to the Pythagoras theorem, AP squared, that is the square of the hypotenuse, equals to AO squared plus CP squared. Actually, this letter is C, so AP squared equals to AC squared, AC squared plus CP squared. AP is 5, therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave this is this. So it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, if you found out that 25 equals to AC squared plus 16. Here we will subtract 16 from this equation. If we get that 25 plus 16 is 9, equals to AC squared. So AC squared equals to 9 here. We take out all those equations and we get that there is inside AC is equal to the square root of 9 units inside, that is to say it is equal to 3. Okay, this is inside AC is equal to 3 units inside. AC equals to 3 units inside. The next step, we define the center of this circle. This point is point O. We define the radius of this circle as x. And we join points O and B together by straight line. Point B is the point of tendency PB with this circle. Point O is the center of the circle, point B is the point of the circle itself, therefore B is the radius of the circle, that equals to x. The radius OB is equals to x, the radius OB is known to point B, that is the point of tendency PB with this circle. And whenever your radius is known to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to all three. PB is a tangent to the circle at point B, so PB is a tangent is absolutely straight line. If you focus on the upper side of the straight line PB at point C, or the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line PB at point C, we have this angle that is the right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say from point O, that is the center of the circle, from point O, that is the center of the circle, we will draw perpendicular on AC. So okay, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. By doing this construction, we can do quadrilateral OMCB. Quadrilateral OMCB, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, into that must be equal to 360 degrees according to the rule that says the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. 270 degrees plus 90 degrees is 360 degrees, that is the sum of the angles in any quadrilateral. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral OMCB we have 4 angles, therefore we can write to quadrilateral OMCB is 30 angles. But we also know that the opposite sides of rectangle are equal to each other. So rectangle OMBC, side BC must be equal to the opposite side OM, but BC is 1, therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the symbol in the same rectangle OMCB, side OB must be equal to the opposite side MC. But OB is X, therefore the opposite side MC must be also equal to X units in its line. What is the length of this? What is the length of this missing line segment? Line segment AM. AM equals to AC minus MC. AM equals to AC minus MC. So AM in total equals to AC, that is 3. Minus MC, that is X. So in total we should find out that AM equals to 3 minus X units in its length. This is the missing side AM. This equals to 3 minus X units in its length. In the next step, we will join points O and A together by side line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of this circle, that equals to X. In the next step, we will implement the Pythagoras theorem on this right green triangle AOM. Here by PT is a abbreviation for Pythagoras theorem. This triangle or AOM, OA squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. And again, this triangle AOM, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AM squared plus BM squared. AM squared plus OM squared. OA squared equals to AM squared plus OM squared. OA is X, therefore OA squared is X squared. And it is equals to AM squared. AM is 3 minus X, and therefore AM squared is 3 minus X squared. Plus OM squared. OM is 1, therefore OM squared is 1 squared, that is 1. So to that, we should find out that X squared equals to 3 minus X squared plus 1. So X squared equals to 3 minus X squared. 3 minus X squared equals to 3 squared, that is 9. Plus X squared minus 2 times 3 times X, that is minus 6X plus 1. So here we have X squared on both sides of the equation, so X squared gets cancelled. After I cancel X squared, this side of the equation left is nothing, that is to say 0. While in the other side of the equation, we have 9 plus 1 is 10, plus 6x. So in total, we should find out that 0 equals to 10 plus 6x. Here, we add 6x to this equation, and find that 6x equals to 10. Here we divide this equation by 2, so we get that 3x, 6x over 2 is 3x, and it is equal to 10 over 2, that is 5. 3x equals to 5, here we divide the equation by 3, and we get that the radius x of the circle is equal to 5/3. And again, we should find out that the radius The radius of this circle x equals to 5 hertz. X equals to 5 hertz. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, and therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 5 hertz, therefore x squared equals to 5 hertz squared. So in total, the area of our circle must be equal to pi times 5 hertz squared. So it is pi times 5 hertz squared. 5 hertz squared equals to 5 squared is 25, over 3 squared is 9. Okay, so in total, we should find out that the area that we're looking for in this question, that is the area of the circle, is equal to either 25 pi or 9 square inches in size, or in terms of numbers, it is equal to 8.73 square inches in size. And again, we should find out that the area that we're looking for in this question, that is the area of the circle, is equal to either 25 pi or 9 square inches in size, or in terms of numbers, the area of this circle equals to 8.73 square inches in size. So, finish with the second question. In the next step, I will summarize the lecture. That is to say, I'll repeat on the first solution with the two methods, and then I'll repeat on the second solution, with the second question. Our task in the first question is to find out the area of the screen shape. So, we know that AD equals to DO, OB equals to 2, this is again DCB, this is right again. So our task is to find out the area of this screen shape. The area of the screen shape is actually the area of this green rectangle, DCB. So we have to find out the area of the green rectangle, DCB. First of all, AOB is a quarter circle, and therefore this is the right angle. Likewise, OB and OA, they are both the radius of the quarter circle, that equals to 2, therefore the radius of OA also equals to 2 units in its length. The radius AO is intersected into two halves at this point D. So the first half AD must be equal to 2 over 2, that is 1, and of course it equals to the second half of AO, that is DO, and it equals to 1. In the next step, implement the Pythagoras theorem on this right line DBC. According to the Pythagoras theorem, in this right line DBC, dB squared, that is the square of the hypotenuse, equals to dC squared plus CB squared. This is the right line DOB. We implemented the Pythagoras theorem on this right line DB. According to the Pythagoras theorem, in this right line DOB, dB squared equals to DO squared plus OB squared. And again, in the right line DOB, dB squared, that is the square of the hypotenuse, equals to DO squared plus OB squared. dB is the missing side, so it is, and it equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, so OB squared is 2 squared, that is 4. So today we found out that dB squared equals to 1 plus 4, that is 5. So dB squared equals to 5. Here to go out of the division, I hold on the missing sign. To go out of the equation, I hold on the value of the bonus dB equals to the square root of 5 minutes instead. This is the missing hypotenuse dB that equals to the square root of 5 minutes instead. The next step, we completed this quarter circle to a circle, and then we extended the radius below by sideline until it touches the circle at this point. We define the touching point of the extended radius below with this circle. This point is point P. The radius BO is a radius, it is absolutely sideline. When you extend a sideline by sideline, the result BP must be also straight line. So BP is a sideline, but BP is a straight line that touches the circle those 2 points, P and B. And therefore, PB is a chord. PB is a chord that passes from point O, that is the center of the circle, and you know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, chord PB is the diameter of the circle. Likewise, we extended the radius AO by sideline until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. So here point O is the center of the circle, point P is the point of the circle itself, therefore P is the radius of the circle, that equals to 2. Likewise, point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is also the radius of the circle, that equals to 2. Moving to the Pythagoras theorem, if we implement the Pythagoras theorem on this right line PDO, 2 squared plus 1 squared is 5 equals to PD squared. We take out of this equation, find out the therefore the hypotenuse PD is equal to the square root of 5 minutes since 9. The next step, we implemented the Pythagoras theorem, we implemented all 24 in our drawing. According to all 24, if chord AB intersects with chord CD at point O, then AO times BO equals to CO times DO. Again, in the drawing circle, this is chord AB that intersects with this chord CD at point O. So in doing drawing, the following equation is told that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 24 in our drawing. I put in our drawing. This is called AQ, that intersects with this called CP at point D. CP is a chord because of the fact that when you extended the sideline CD by sideline, there is not CP as a sideline. So CP is a sideline that touches this semicircle at those 2 points C and P, and therefore CP is a chord. So, according to all 24, chord AQ intersects with chord CP at point D. So all the requirements for full 24 are satisfied, and therefore we can implement all 24 in our drawings. According to all 24, AD times DQ equals to CD times DP. And AD times DQ equals to CD times DP. AD is 1 times dq. dq is 1 plus 2, that is 3, and it is equals to cd. cd is the missing sign, so left as it is, times dp. dp is equal to 5. So in total, we should found out that 1 times 3 equals to cd times square root of 5. 1 times 3 is 3, so 3 equals to the square root of 5 times cd. Here we divided the equation by square root of 5 and found out that the missing sign cd equals to 3 over square root of 5 minutes instead. This is the missing side CD that equals to 4 over square root of 5 minutes in its length. In the next step, we implemented the Pythagoras theorem on this right great line DCB. According to the Pythagoras theorem, in this right line DCB, dB squared, that is the square of the hypotenuse, equals to dc squared plus cb squared. And again, this right line dB, according to the product theorem, dB square equals to dO square plus OB square. Actually, this is the right triangle dCB. This right triangle dCB according to the right triangle dCB according to the product theorem, dB square, this is the square of the hypotenuse, equals to dC square plus CB square. Again, right triangle dCB according to the product theorem, dB square, this is the square of the hypotenuse, equals to dC square plus CB square. dB equals to the square root of 5, and therefore dB square square root of 5 square, that is 5, and it is equals to dC square. dC is 3 over square root of 5, and therefore dC square is 3 over square root of 5 square, that is 9/5, plus CB square. CB is the missing side, so here it is. So in total, we found out that 5 equals to 9/5 plus 9/5 plus CB square. Here we multiply 5, and then we divide it by 5 in order to overcome a factor with this number. So 5 is 25 over 5, and it is equals to 9/5 plus CB square. Here we subtract the 9/5 from this equation, and we found out that 25/5 plus 9/5 is 16/5 equals to CB square. Here to go down to the equation, and we found out that the missing side CB equals to 4 over square root of 5 minutes inside. So this is the missing side CB is equals to 4 over square root of 5 minutes inside. Our task is to find out the area of the green shape. The area of this green shape. The green shape is actually the green right triangle dCB. So we have to find out the area of the green right triangle dCB. And again, our task is to find out the area of the green shape. And the green shape is actually the green right triangle dCB. So we have to find out the area of the green right triangle dCB. The area of this green right triangle dCB equals to the base DC times the height CB over 2. Which again, the green right triangle dCB in total is equals to the base DC times the height CB over 2. DC is 4 over square root of 5 times CB is 4 over square root of 5 divided by 2. So here we have 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. So in total, the area of the green shape equals to the value of this expression. This expression in total equals to 3 over 4, that is 12. Square root of 5 times square root of 5 is 5 divided by 2. We move to the denominator. So in total, this expression equals to 12 over 5 times 2, that is 10. So the area of the green shape in total equals to 12 tenths. Or in terms of numbers, it is equals to 1.2 square units in size. So finish with the first method. And the next step, repeat on the solution according to the second method. That is to say, we find out, repeat on the solution of the second method. Now we found out that the area of this green shape is equal to 1.2 square units in size according to the second method. EOB is a quarter circle, and therefore this is the right angle. Likewise, OB and OA, they are above the area of the quarter circle, that is equals to 2. So the radius AO equals to 2. At point D, the radius AO is bisected into 2 halves. Each half must be equal to the length of the radius over 2. That is to say, each half must be equal to 2 over 2, that is 1. So the first half it is 1, and the second half of the radius AO must be also equal to 1 unit in its length. So in the next step, we completed this quarter circle to a semicircle. Then we extended the radius BO by straight line until it touches the semicircle at this point. We define the touching point of the extended radius BO with this semicircle. This point is point P. So the rules BO, it is absolutely a straight line. When we extend the straight line by straight line, the result BP must be also a straight line. But BP is a straight line that touches the semicircle and those 2 points P and B, and therefore BP is a chord. BP is a chord that passes from the center of the circle, that is to say from point O. And therefore, we know that any chord that passes from the center of the circle must be the diameter of the circle. Chord PB passes from point O, that is the center of the circle, and therefore chord PB must be the diameter of the circle. Okay. So here we have this again equals to 90 degrees inside according to rule 3. In the right triangle PDO, 2 square plus 1 square equals to PD square. 2 square plus 1 square is 5, so 5 equals to PD square. To wrote out of the equation, if I follow the left of the hypotenuse PD is 4 to 5 units in its length. The next step, define this angle DPO as alpha. So in the small right triangle DPO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in any triangle. Likewise, in the this first missing angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. So this first missing angle must be equal to 90 degrees minus alpha. The small right triangle PDO is similar to the big right triangle PCB according to angle similar to. That is to say, this is the angle alpha, that is the common angle that belongs to both triangles, so we can write down that angle alpha equals to itself is the common angle that belongs to both triangles. Likewise, those two angles are both equal to 90 degrees and therefore they are equal to each other, and finally those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if we prove that all the figures of this small right triangle PDO are corresponding equal to all the figures of this big right triangle PCB, and therefore those two right triangles can go into each other according to angle similar to. And again, if you know that the small right triangle PDO is similar, this is the sum of similar to the big right triangle PCB according to angle similar to. And for the fact that the small right triangle PDO is similar to the big right triangle PCB, we will derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle PDO over side PB of the big right triangle PCB equals to side DO of the small right triangle PDO over side CB over side CB of the big right triangle PCB, and it is also equal to side PO of the small right triangle DPO over side PC of the big right triangle PCB. PD is equal to 5, PB is 4, DO is 1, CB is the missing side, so we write it as it is, PO is 2, and PC, this is side PC, in total it is equal to the square root of 5 plus DC. And again, PC equals to the square root of 5 plus DC. So in total, if you found out that the square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other. Therefore, we can get the equation 1 from those two sides that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. And again, according to equation 1, square root of 5 over 4 equals to 1 over CB. Here, of course, multiply this equation, if I found out that 1 times 4 is 4, so 4 equals to this, 4 equals to the square root of 5 times CB. Here we divided this equation by square root of 5, and we found out that the missing side CB is equal to 4 over square root of 5 units in its length. This is the missing side CB is equals to 4 over square root of 5 units in its length. Those two sides of the equation are equal to each other, therefore we can do the equation 2 from those two sides that are equal to each other. So according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Then according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here, of course, multiply this equation and equation 2. Find that according to this equation and equation 2, 4 times 2 is 8 equals to the square root of 5 times square root of 5 plus DC. Here, open the brackets of this expression and find out that 8 equals to the square root of 5 times square root of 5 is 5 plus square root of 5 times DC. Again, because I found out that 8 equals to the square root of 5 times square root of 5 plus DC. So 8 equals to square root of 5 times square root of 5 is 5 plus square root of 5 times DC. So total according to equation 2, if you found out that 8 equals to 5 plus square root of 5 times DC. Here we subtract 5 from this equation and found out that 8 minus 5 is 3. So 3 equals to the square root of 5 times DC. Here we divide this equation by square root of 5 and find out that the missing sign DC equals to 3 over square root of 5 and it's inside. That's inside DC. This equals to 4 over square root of 5 and it's inside. Our test is to find out the area of the green shape, this green shape. The green shape is actually the right green triangle DCB. So our test is to find out the area of this green right triangle DCB. So we have to find out the area of the green shape, and the green shape is actually the area of the green shape equals to the area of the green right triangle DCB. So the area of this green right triangle DCB is equal to the base DC times the height CB over 2. And again, the area of the green right triangle DCB equals to the base DC times the height CB over 2. DC is 4 over square root of 5, CB is 4 over square root of 5 divided by 2. 3 times 4 is 12, square root of 5 times square root of 5 is 5 divided by 2. 12 over 5 over 2 equals to 12 times 5 times 2. And it is 12, and 5 times 2 is 10. So it is 12 times. With also numbers, I should know in both methods that the area of this green shape, in total it is equal to 1.2 square units in size of both methods. Okay, so finish with the first question. The next step I put on the solution of the second question. In the second question, our test is to find out the area of this circle. So the goal with a circle that intersects with this right triangle ACP at those 2 points. In addition, we know that this is line 7CB, this is equals to 1 unit in itself. This is line 7CP, this is equals to 4 units in itself. This is angle ACP, that is right angle. In addition, we know that this is a common external point, point P. Point P is the common external point in relation to this circle. For the common external point, point P, we have 2 tangents to this circle. Tangent PA and tangent PB. And for the 2 are equal to each other. This is to say PA equals to PB. According to 2, tangent PB equals to tangent PA in its length. And again, according to 2, tangent PA equals to tangent PB in its length. But it is given us the question that the left is given us the question that the length of this tangent PB equals to 4 plus 1, that is 5. So you can write here that PB equals to 5, and from this equation PA equals to PB equals to 5, we derive that PA must be also equal to 5 units in itself. This is tangent AP, this equals to 5 units in itself. In the next step, we have provided the Badrow's theorem on this right triangle ACP. And this right triangle ACP, according to the Badrow's theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. Okay, again, the right triangle ACP, according to the Badrow's theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, therefore B squared is 5 squared, that is 25. And it is equals to it is equals to AC square. AC is the missing side, so it is, plus CP square. CP is 4, therefore CP square is 4 squared, that is 16. So in total, we found out that 25 equals to AC square plus 16. Here we subtract 16 from this equation, if I found out that 25 from 16 is 9, equals to AC square. Here we took out of the equation, I found out that the missing side AC equals to the square root of 9, that is 3. This is the missing side AC, that is equals to 3 units in its length. The next step, we define BP is a tangent to the circle, so BP is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line BP at this point C, here the sum of the areas must be equal to 180 degrees according to all three. All three states that the sum of the areas of one side of the straight line is equal to 180 degrees. So which angle here with the upper side of the straight line BP at point C, we have this angle that is right angle, plus this missing angle, in total the sum of those angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we define the center of this angle, this point is point O. We define the radius of this angle as x. Then we join point O and B together by straight line. Point O is the center of the circle, point B is the point of the circle itself, therefore B is the radius of the circle is equal to x. Point B is the point of tendency of tangent PB with this circle. The radius of B is equal to x, the radius of B is drawn to point B, that is the point of tendency of tangent PB with this circle. Remember, your radius is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to 1. So in the next step, we did the construction. That is to say, from point O, we look perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point N. By doing this construction, we can derive quadrilateral OMCB. In quadrilateral OMCB, we have 1, 2, 3 areas. The sum of 3 areas is 270 degrees, so 270 degrees plus the size of this four pieces again. In total, it must be equal to 360 degrees according to all that sets. Then the sum of the areas in the quadrilateral is equal to 360 degrees. And therefore, this four pieces again must be equal to 90 degrees in its size. So in quadrilateral OMCB, we have 4 areas, and therefore quadrilateral OMCB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM. But BC is 1, therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the same rectangle OMCB, side OB must be equal to the opposite side MC, but OB is x, therefore the opposite side MC must be also equal to x units in its length. What is the length of this line segment AM? AM equals to AC minus MC. AM equals to AC minus MC. So AM equals to AC, that is 3, minus MC, that is x. So in total, AM equals to 3 minus x units in its length. In the next step, we join points O and A together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of the circle, that is equal to x. So we implemented the Pythagoras theorem on this side line OAM. According to the Pythagoras theorem in this side line OAM, OA square, that is the square of the hypotenuse, equals to AM square plus MO square. The upper right hand line AOM, OA square, that is the square of the hypotenuse, equals to AM square plus OM square. The hypotenuse AO equals to x, and therefore AO square is x square, and it is equals to AM square. AM is 3 minus x, therefore AM square is 3 minus x square, plus OM square. OM is 1, so OM square is 1 square, that is 1. So in total, if we have x square equals to 3 minus x square plus 1. So x square equals to 3 minus x square equals to 3 square, that is 9, plus x square minus 2 times 3 times x, that is minus 6x plus 1. We have x square on both sides of the equation, so x square will be cancelled, so x cancelled x square. In this side of the equation, we have nothing, that is to say 0, and on the other side of the equation, we have 9 plus 1, that is 10, minus 6x. So total, if you found out that 0 equals to 10, minus 6x. Here we added 6x to this equation, if I found out that 6x equals to 10. So here we divide this equation by 2, if I found out that 6x over 2 is 3x equals to 10 over 2, that is 5. So in total, if you found out that 3x equals to 5. Here we divide this equation by 3, if I found out that x equals to 5 thirds. And again, the radius of this circle x equals to 5/3 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, and therefore the radius of our circle squared must be equal to x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 5/3, and therefore x squared is 5/3 squared. In total, the area of our circle must be equal to pi times 5/3 squared. So it is pi times 5/3 squared. 5/3 squared equals to 5 squared is 25, over 3 squared is 9. So in total we found out that the area that we are working for this question, that is the area of this circle, equals to either 25 pi over 9 square units in size. In terms of numbers, the area of this circle equals to 8.73 square units in size. Okay, thank you very much.